Hey there, in this video we're going to discuss a little bit about binary logistic regression. Binary logistic regression is used when we have a dichotomous dependent variable. So our dependent variable only has two values, say 0 and 1. That's a situation where we would want to use a binary logistic regression. We wanted to predict, say, membership in, say, group 0 or 1. As always, start with the README page here. It gives the readings in the book. So the Logistic and Fidel, chapter 10, goes into a lot of detail about logistic regression. I'm going to walk you through my notes on logistic regression. And then I also have two optional readings that you might find helpful. This is a great just introductory article on logistic regression that I think you might find helpful. It talks a lot about interpreting logistic regression coefficients and then how you actually report the results from a logistic regression analysis. And here was just another good overview of logistic regression that I found online. You can download both of these articles in this zip file right here. You can also download my notes on logistic regression right here, and then the non-textbook readings, those two articles I talked about here. I've posted a video on where I walk through logistic regression and SPSS, so you can see that video on Canvas as well. It should take you to the YouTube link for that. I've also posted my annotated output for walking through a logistic regression in SPSS. So you can see here's the steps to conduct the logistic regression, how you would click through the SPSS menus. Here's another way you can get another estimate of R² for your binary logistic regression model. We'll talk about that in a little bit. And here's kind of the example that we go through, and you can see the output is annotated, kind of what each one of these tables is telling you. I've posted an example write-up for logistic regression, so you can see how how you would present the results from a logistic regression analysis. So you can see that here. You'll find it on here as well. And then the assignment for this week, you have a data analysis assignment and a quiz, as we do in every module. And you can see the data analysis assignment is very similar to the example that we go over. In this one, I don't have you writing up the results. It's a little more involved in logistic regression, but you can see we're kind of hitting the main points in this assignment. If anything's unclear in the assignment, please email me and let me know, or post a question to the message board, and I'll try to clear up any confusion you might have. So I just want to take a few minutes and talk about, kind of review some of the notes on logistic regression. Let me zoom this in. So, thus far we've really talked, all the dependent variables we've used have been continuous. So they were measured on either an interval or ratio scale. And we've used various forms of the general linear model to assess the relationship our independent variables have with our dependent variable. However, there are situations where a dependent variable may be dichotomous, so it only has two possibilities. It could be, whether someone was in one group or not, whether you have a disease or you don't. And so we're wanting to maybe predict group membership. In these cases, linear models really aren't appropriate. One reason is that for a linear model, there's no restriction on the range of the predicted values. So we can predict values greater than 1 or values less than 0, and that's not really ideal. If you remember from OLS regression, the general linear model made an assumption that the residuals were normally distributed with a constant variance. That's that homogeneity of variance or homoscedasticity in OLS regression. In a binary case, the residuals won't be normally distributed or have a constant variance. So for those reasons, we're going to use what's known as a generalized linear modeling approach for modeling non-continuous dependent variables. In the generalized linear modeling approach, the basic idea is that we're specifying a link function that transforms the dependent variable so that the predicted values are constrained to be within some specific interval. And for when we have a dichotomous outcome, we typically use what's called a logit link function, and that's where the name of the analysis, logistic regression, comes from. There's a related analysis called probit regression, I'll mention briefly in the notes, where it uses a probit link function to constrain the values to be between 0 and 1. So, logistic regression is really used when our dependent variable is binary and we're wanting to predict, whether you're in group 1 or group 0, or group 1 and 2, or whether you have a disease, you don't have a disease, whether, say, a student is retained or not retained, whether a student had to repeat a grade or didn't repeat a grade. And we want to know, can we explain this, whether their group membership, given their pattern of responses on a set of independent variables. So this equation here, I'm trying to sort of demonstrate this linking function here. So really we're modeling the probability that we're in y equals 1, so we're in group 1, by using a nonlinear logit function to model the probability of that you're in group 1 divided by the probability that you're not in that group. So it's basically the natural log of the probability of being in one group divided by the probability of not being in that group is then a function of this linear combination of independent variables. These logistic regression is estimated using what's called maximum likelihood procedures. So we are maximizing the likelihood of observing the data that we have. So the coefficient estimates that we receive then maximize then the probability of actually observing the data that we've observed. So just some different assumptions and practical issues that you should take into consideration running a logistic regression. And we're not going to check all of these in our example, but it's good to kind of know for future reference. Basically with all types of modeling situations, we assume that the model is correctly specified. And this is where it's really important to know the literature on your subject and where you take into account previous findings, previous research, and any theoretical considerations to make sure that your model is actually correctly specified. We have an assumption of independence here. We assume that, responses come from different cases, basically. We assume there's a linear relationship between the continuous predictor and the logit transformation of the dependent variable. And Tabachnik and Fidel in their chapter talk about this Box-Tidwell approach that you can use to assess this assumption. Basically, you create an interaction term between your continuous variable and the natural log of that continuous variable, and then you add that interaction term to the model, and if that interaction term is significant, it indicates a violation of that assumption. Just like in OLS regression, we assume that our independent variables are measured without error. And this is probably violated to some extent, especially in behavioral and social sciences, where we don't have perfect measures of all of our predictor variables. Notice logistic regression does not make an assumption regarding the distribution of the residuals. Like in OLS regression, we assume that the residuals were normally distributed with a constant variance. Logistic regression doesn't make that assumption. However, multivariate normality may actually enhance the power of your model, but it's not actually required. Note that logistic regression requires a larger sample size than typical OLS linear regression. Basically the larger the sample size, the better. Typical rules of thumb you might see are around maybe 20 cases per independent variable. But there's also issues of empty sample sizes and cell sample sizes. So if you have a categorical variable, say you had like males, females, you want to make sure that you have, some successes and some failures within each one of those categories, if that makes sense. So, if your outcome is coded 1, 0, you want ones and zeros, a good number of them in each cell of that categorical variable. You can, run some crosstabs on your data to make sure that occurs. If not, you could get some unstable estimates, so the model may not even estimate. There's another issue related to that's called separation or quasi-separation, and that's where the outcome doesn't vary at some level of the independent variable. That would be if, all females happen to be retained. Well, then we couldn't really use females in the model because they don't, or use gender in the model really, because they don't vary with respect to our dependent variable. Multiclinearity is also an issue in logistic regression. Remember, multiclinearity is the idea of the interrelatedness of the independent variables, how intercorrelated are the independent variables. For some reason, SPSS doesn't give you collinearity diagnostics in the logistic regression command by default, or you can't even ask for them really. So, basically what you have to do is just run your same logistic regression model as an OLS regression model, as a linear regression model, and just request variance inflation factors, and you kind of use the same rules of thumb that you had in OLS regression there is how you would typically assess multiclinearity. So interpreting the coefficients in logistic regression isn't as they're not as nice and interpretable as they were in OLS regression. Remember, in OLS regression, we interpreted the unstandardized coefficient as a 1 unit change in our X variable corresponded to a B unit change in our outcome. So in logistic regression, we're modeling the log odds. We're modeling a logit. Remember, we made this logit transformation to our dependent variable, so that then kind of complicates the interpretation of our regression coefficients. So instead, we would interpret the unstandardized coefficient in logistic regression as the rate of change in the log odds of success in Y. So the log odds of Y equal 1 as X changes. So these aren't very informative. So typically what people do is exponentiate this coefficient and transform it into an odds ratio. And odds ratios, I would say, are a little bit more interpretable. You just kind of have to wrap your head around what an odds ratio is. It's a ratio of two odds. So it's the change in the odds of being in one category of the outcome when the value of the predictor changes by 1 unit. So if we have an odds ratio, say our odds ratio is 2.1, that would indicate that the odds of being in group 1 are 2 times higher when X is 1 compared to when X is 0. So it's still a 1 unit change in X. Our 1 unit change in our independent variable corresponds to a 2.1 unit increase. Well, a 2.1 increase rather, a 2.1 increase in the odds of being in Y equals 1. So when an odds ratio equal to 1 indicates that there's no relationship. An odds ratio greater than 1 indicates a positive relationship, and an odds ratio less than 1 indicates a negative relationship. So if you had an odds ratio of 0.8, then that would indicate that a 1 unit change in the predictor variable, so going from 0 to 1 or from 1 to 2, corresponds to a 20% decrease in the odds of Y equals 1. So remember, we're trying to predict whether, that's what we're talking about, the success in Y, whether you were in the group labeled Y equals 1. So what are the odds that you're going to be in there? If the odds ratio is negative, it's saying that increasing on the predictor variable means that you're decreasing in your odds of being in that group. Sometimes it's easier if you have an odds ratio less than 1 to take the inverse of the odds ratio and then flip your comparison group, especially if your indicator variable is categorical. So you just flip the indicator in the reference group, take the inverse of the odds ratio, and then that would give you, it would put it in, it would put the odds ratio to be greater than 1, and then you would interpret it as going from the reference group to the indicator group would indicate that increase in the odds ratio. And I talked about that in the example. We have an odds ratio less than 1, so I take the inverse of it, and then we flip the reference group to interpret it. The odds ratios are also a measure of effect size for your individual predictor. So the larger the odds ratio, the stronger the effect for that individual predictor. This was a good article I found online that that I thought did a really good job of explaining odds ratios. So I thought I'd link to it in here for you. I think another useful way, because odds ratios can really get messed up in your head sometimes. Remember, it's an increase in the odds of success in Y. Instead of interpreting just the logistic regression coefficient or the odds ratio, we could transform the regression coefficient into a predicted probability. And sometimes that's more interesting, especially if we have some some hypothetically or strategically important case, and we want to know, if say we want to look at, the probability males and females would be in, would be retained. Say retention is our outcome. So we want to know whether they're going to be retained or not retained. We can look at the difference between males and females. We say, well, if they're held constant on all of these other variables in the model, how would then changing, whether they were male or female, what are their what's the probability that they'll be in the retention group, or the probability that they'd actually be retained. We can calculate the predicted probability. Basically, all we're doing is we're converting then these log odds into probabilities. This is the probability of success, and this is the probability of failure. Essentially, the probability you're in y equals 1, the probability you're not in there, which would just be 1 minus that probability. So we're taking this log odds and then basically solving for p here. So we could exponentiate both sides, and we would come out here. We could then factor this out, and we would have. So you could use either one of these formulas. So we solve for our logit, and then to calculate the probability, we'd insert our logit into one of these formulas. Notice if you're using the shorter formula, you take the opposite sign of the logit. It has a negative sign there. I just wanted to point that out. If we look at the example, let's pull it up and I'll show you kind of what I'm talking about, how I solve one. So here we're looking at the predicted probability of being an honors composition for basically someone who has an average reading score compared to someone who has a reading score who's like 1 standard deviation above average. And then who, for basically, we have to pick a value for the other variables in the model. So we're going to say they have average science ability scores and medium SES. So we would solve our logistic regression equation, which is given in our coefficients estimates here. We have a constant, 0.066 times science, 0.098 times reading, minus 1.0313 times SES. I think this was medium SES. And so you would solve then the regression equation for that. So someone who has average reading, average science, and who's in the medium SES, so they have 0 in the first one, 1 in the second one. Here's their logit. We then put the logit back into, to solve for the predicted probability. We take the inverse of the sign of it and fill out the formula, 1 divided 1 plus e to the negative logit. And so someone who has an average reading score and who has average science scores and medium SES would have an 8% probability of being in the honors composition course. And so we could compare that to someone who has an above average reading achievement score. So that'd be someone with, say, a 60 in reading. I think that's 1 standard deviation above the mean in these data. So we would just change that part. If you notice that these two equations is the only part that's different, we would get the predicted logit from the model and then solve for the probability. So someone who had a reading score of 1 standard deviation above the mean would have a 20% probability of being in the honors composition course, where they're the same on the other. So you can kind of play around some with the model. These are the, what would be the predicted probability of the model? What is the model predicting their probability of being in, in this case, it was honors composition course. So that's what I mean by these predicted probabilities here. So you would solve the regression equation for the logit, and then you're going to back out the probability out of here. So if that wasn't confusing enough, trying to get an estimate of variance explained in logistic regression is a complicated concept. There's no direct equivalent to R squared from linear regression in logistic regression. So people have developed several what we call like pseudo R squared values that attempt to try to get at this idea of variance explained in OLS regression, but none of them can really be interpreted exactly like OLS exactly like the R-squared value in OLS regression. They're really just rough estimates of what the variance explained might be. SPSS currently reports 2 pseudo R-square measures for you by default. And then here I'll show you how you can calculate 2 additional ones. The Cox and Snell R-square value. And then I always butcher this name, so I'm not going to even try. Which is really an adjustment to the Cox and Snell R-square value. And then this Nagertle's R-square value will always be a little bit higher than the Cox and Snell value. I think Tabachnik and Fidel have a really good write-up on these different pseudo R-square values. And here's another link to another really good write-up on lots of different R-square values. One that I'm particularly fond of that you have to calculate it by hand in SPSS is with this article down here called Efron's R-square value. And it's basically the square of the correlation between the model's predicted values and then actual values. And I like this approach because it really mimics what's done in OLS regression. And this is where the term R-square comes from in OLS regression. We're squaring the correlation between the model's predicted values and then the actual values on the outcome. And so we can do the same thing in logistic regression. I'll show you how in the example, how it will save out the predicted values and then basically just run a regression, or we could do a correlation between the predicted and the actual values and then square that correlation. If you run them as a regression, it's going to square the correlation for you automatically. I like it because it's intuitive. It's just the squared correlation between the predicted and the actual values, but it does have some limitations in logistic regression. You know, one thing would be is, you know, if you had the predicted values were 0.49 and 0.51, that there's a small difference in what their predicted probability would be in each group membership, but the model would classify them into 2 separate groups. Usually our cutoff for classification is 0.5. Anything higher than 0.5 is classified as a success or classified as 1. Anything less than that, anything that the model predicts less than 0.5 would be classified as a 0 or not success. And so while their predicted values are the same, and then the squared correlation between their actual value would be very similar, the model is going to classify them into different outcomes. So that's a bit of a limitation of this model. Tabachnik and Fidel also talk about and advocate for this McFadden's R-square value. SPSS doesn't provide this one for you by hand, but it's really easy to calculate. It's just 1 minus the ratio of the deviances or the log likelihood of your full model and your null model. A lot of people like this R-square value because it has a nice interpretation as the proportional reduction in error variance. So, you basically take the log likelihood value of the null model and then the log likelihood value of your full model. And so it's saying that our full model has reduced the error variance of our null model by whatever percentage. So in our example, it was like 28.3. So our full model has reduced the error variance of the null model by about 28%. And then if you read in the Tabachnik and Fidel book, you'll see how the Cox and Snell and the other R-square value here are really just corrections to the McFadden's R-square. Cox and Snell take into account, it's basically McFadden's R-square, and it does a little adjustment to it to adjust it for sample size. which then has a limitation that the maximum value of Cox and Snell can't be 1. So the Nagerle's R square value here makes an adjustment then to Cox and Snell so that the maximum value can be actually equal to 1. So you could read about those here in Tobias and Cadell or in this, this really cool handout here I found too. You know, sometimes we want to know how well does our model actually fit the data? How well does it do it? How well does our model do a good job of explaining the relationships in the data that we have? And so there's a couple different ways we can assess this in logistic regression. One of them is just a classification table. So SPSS will print this by default. And it's basically the proportion of cases that we correctly classified as 0 and 1. One thing that we want to see is that our full model is doing a better job of classifying people than our null model. And our null model is typically a model with no predictor variables at all. So basically, if we just guess that everybody was in one group, how well is our model performing? Versus if we try to model the relationship these independent variables have with this outcome, how well is our model doing at predicting group membership? And we want to see how well our model is doing overall, and then how well is our model classifying people into group 0 and into group 1. How well is it doing classifying, you know, people as maybe having a disease or not having a disease? In the example we got in here, how well is it doing classifying people who are in honors composition course versus those who are not in the honors composition course? Another goodness of fit measure is this Holmesmer-Leemshow statistic. And it basically evaluates how well our model is fitting our data by basically ordering the cases based on the model's predicted probability, dividing these into like 10 different groups. And, you know, it's basically looking at, you know, we should have, you know, the cases, you know, most cases who are not in, who are not in honors comp should be in the lower deciles, right? And those who are in honors comp should be in the higher deciles. So it's basically saying how well is our model predicting actual group membership. And so this is basically like they perform like a chi-square statistic on this. You'll see in the output, it's like a little like contingency table from, you can see, so this is what we observed, how many people were in, or this would be not in honors comp, how many we observed, and then what do we expect based on the model. So you can see it's kind of like a 2 by 10 contingency table. Remember those from like goodness of fit contingency table from stats 1. And you know, this follows a chi-square distribution. So this is one where we want to fail to reject the null hypothesis that says that our model fit our data pretty well. And if we fail to reject this, if we reject this statistic here, we could use this contingency table to kind of diagnose the area of misfit. You know, we had 14 observations in this decile, but our model's only predicting or expecting 3. You know, that's a source of misfit. Here, all the numbers are fairly close from what we observed and what we expected. That's why the chi-square statistic is not statistically significant. Holmesmer-Leemshow also have a very popular textbook on logistic regression. So if you're interested in learning more about logistic regression, I'd highly recommend their textbook on the subject. We could also use the model's likelihood function to kind of compare 2 models that are nested with each other. Say we're trying to decide whether or not X, you know, one variable should or shouldn't be in the model. We could do that by comparing the likelihood function for each of the models. So a model that had the predictor X and a model that doesn't have the predictor X. And basically the model with the lowest log likelihood fit the data better than a model with higher likelihood values. You could also test there's also a formal test you could use. It's called a likelihood ratio test, where we take the difference in the two log likelihoods, the difference between two log likelihoods, and then the difference in the number of parameters between each model would follow then a chi-square distribution, with the difference in the number of parameters in the model would be the degrees of freedom for the chi-square test. And SPSS performs this test for you automatically, basically comparing your null model, so the model with no predictor variables in it, and then the model, your full model with all of your predictor variables in it. So it's saying that do all of these predictor variables as a set, do a better job of explaining group membership in the model with no variables in there. So you want to see that that model is statistically significant. But you could also do it, it's kind of a block entry approach too, where we'd enter variables into the model at certain blocks. And instead of how we would assess like the change in R square in LLS regression, we would assess the change in the model's likelihood function. And then the model with the lowest likelihood function fits the data better. So just some alternatives to logistic regression. I kind of mentioned one of these before. One of them is called probit regression. So instead of using a logic link function, we use a probit link function, which a probit link is really just an inverse normal distribution. And, for most practical purposes, there's not much difference between a probit and a logistic function. If you graph them side by side, I think the tails of the probit function are a little bit fatter at the ends than the logit function, but they tend to produce very similar results. You can see Gilman and Hill here demonstrate that you can either convert back and forth between their coefficients by just dividing by 1.6. So if you divide the logistic regression coefficient by 1.6, you'll get the probit regression coefficient. Logistic regression models are probably the most common way you'll see binary variables treated or modeled, especially in the behavioral sciences and education and psychology. Some fields like economics use probit model. They prefer probit models. So really, I just recommend choosing the the model that would be most familiar to readers in your field. For most of us, that would be the logistic regression model. But if in case you ever see or hear about the probit model, you'll know that it's trying to do the exact same thing as the logistic regression model. And here's a kind of a brief comparison you might find interesting between them. Another thing you might see out there, people will model binary outcomes using what they call a linear probability model. And basically what they're doing is just running a basic OLS linear regression on your binary outcome. Earlier we talked at the beginning of the notes about all the bad things that would happen if you did that. You get predicted values above 1 or predicted values above 1 or predicted values below 1. The residuals won't be normally distributed or have a constant variance. All of those things are still true, but there may be some situations where it's maybe okay to violate those assumptions. Some people will argue that the linear probability model works pretty well if, the proportion of cases are between like 2 and 8, or if your goal isn't really to predict an individual's probability of being in one group or not, then, maybe this isn't a big barrier. There's also some adjustments we can make in linear regression to take into account the violations of normality and constant variance. Even though these assumptions aren't satisfied, your regression coefficients are still unbiased. The standard errors are usually inflated The standard errors are usually biased in some way. And so we can use various forms of robust standard errors if that's the concern. There are some fields where linear probability models are used frequently. I don't see linear probability models used very frequently in education or psychology. But there was a recent article here, different alternatives to logistic regression models in experimental studies in the Journal of Experimental Education, where Francis here argues for the use of the linear probability model, that it's a good alternative to the logistic regression model. So you can read about that if you want a little bit, learn a little bit more about it. Finally, I've linked in here some other helpful resources that you might find helpful, and then some additional videos. Here's another example of walking through logistic regression and SPSS. I just linked to the first part of the video. There's 5 parts to it, and then just a general introduction into logistic regression. So that's my quick overview of logistic regression. Now, as always, if you have any questions or concerns, please shoot me an email. I'm here to help. Thank you, and see you next time.